Volker is professor of philosophy at the University of Oxford and tutorial fellow of New College. Volker is a philosopher who addresses philosophical questions through logical analysis. The focus of his research is axiomatic series of truths. He wrote a much appreciated book about the subject. By the way, a book that I consult regularly. The inquiry into questions of self-reference, intentionality, and syntax series form a substantial part of his recent work. So Volker's talk is titled Self-Reference and Intentionality in Metamathematics. So the floor is now Volker's.
Thank you very much, Albert. I mean, also thanks to Professor Cheng and his team for setting up this workshop. It's a pity that we can't be there in Wuhan. Obviously, it's a nice place and it would be much better to see you all face to face. Then I have to apologize. I'm still struggling with internet connection problems. So if suddenly I should freeze, then you know I'm probably talking to a frozen computer. Okay, so Albert has mentioned the title of my talk. I mean, for starters, this is a fairly programmatic overview of some of the work I have done in order to understand the Gödel incompleteness theorems and the applicability to philosophical issues a little bit better. I have published, or I'm about to publish, or I may publish a couple of papers on this with others. As you can see, a great influence has been Albert, from whom I have learned a lot. So we have written these two papers on self-reference and arithmetic, a paper on Henkin. Then at the moment, I'm also writing a book with Graham Lee, where we don't use arithmetization, as I will do in this talk, but rather syntax theory. I'm working with Balthasar Grabmeier and Ling-Yang Ye on a paper also on self-reference, and that is, I mean, an old project by Balthasar, Bo, and Albert on coding. So, I mean, what I'm doing here is just a very rough overview of, I mean, how I see the situation with intentionality in metamathematics. So here is the plan of the talk. I mean, I'm going to say a little bit about, I mean, what makes a metamathematical result, in particular the Gödel incompleteness theorems, philosophically significant. I introduce the problem of intentionality. I try to locate different sources of intentionality, and the three sources I have in mind here are coding, expressing properties such as provability, then self-reference, and then I end with a conclusion and maybe some questions. Okay, so here's the first section on philosophical significance of metamathematical theories. I will be very imprecise with respect to the arithmetical language and theory I'm using. I mean, from time to time, I have to zoom in and, I mean, fix a particular theory. So, I mean, I think all the, I mean, for most of the time, you can think about piano arithmetic, although occasionally I might have to add certain function symbols to the language of arithmetic. But I mean, for many observations, I mean, a much weaker theory, such as elementary arithmetic or Robinson's Q, will suffice. Okay. So, I mean, obviously, many results in metamathematics have been thought to be philosophically significant. I mean, above all, the Gödel incompleteness theorems. And I mean, the previous speakers have already mentioned how the Gödel incompleteness theorems are. But many of these results depend on what a sentence in the language of arithmetic expresses. Sorry, I can always hear background noise. Could you please mute yourself? Okay. But of course, one problem with this is there might be different sentences expressing a certain meta-theoretic claim. I mean, they might express consistency, for instance, in many different ways. or we may even doubt whether a given arithmetical sentence really expresses what is supposed to say. And I mean, what is very well known is, of course, that many results are very sensitive to how provability is expressed. But here I would like to widen focus and also look at other sources of intentionality. So I thought I'll give you a few examples of versions of mathematical results in their, I mean, what I call here philosophically usable forms. I mean, I do not claim that these claims below are correct, and they're certainly not precise. So, I mean, people might use something like no theory extending piano arithmetic proves its own consistency, something like this. A sentence stating its own unprovability in Q is independent in Q, and it's also true. So this is a version of the first incompleteness theorem. The sentence stating its own provability in piano arithmetic is provable. So that would be a consequence of Löb's theorem, supposedly. The sentence stating its own sigma-1 truth is refutable. The sentence stating its own pi-1 truth is refutable, and so on. So, I mean, all these observations are about a certain arithmetical sentence that is supposed to say something. I mean, as a side remark, I'm also very much interested in claims in extensions of the language of arithmetic. I mean, in arithmetic, we don't have a predicate for truth, of course, because of Tarski's theorem, but we might just augment the language of arithmetic with a truth predicate or a necessity predicate or a knowledge predicate or whatever. And then, I mean, we might prove results about that predicate. And then similar phenomena arise. But I won't go into this, I mean, in this talk. What are the sentences, I mean, meta-theoretic claims that are translated into the language of arithmetic? I mean, for the second incompleteness theorem, we proved that a sentence expressing consistency is not provable. So the sentence in question is piano arithmetic is consistent. For the answer to Henkin's problem, I mean, what about the sentence that states its own provability? The sentence in question is this sentence is provable, and we showed that this sentence is provable. And for partial truth tellers, I'm going to explain exactly how they work. I mean, this would be the sentence in sigma-1 is true. So how are we going to translate this into arithmetic? I mean, first of all, I mean, you might already become nervous because of the use of the definite article, this sentence or this, yeah, I mean, in these formulations, this sentence stating its own provability, or this sentence stating its own sigma-1 truth. People talk like that very often in philosophical discussions, but that's, of course, I mean, an extreme simplification, because there are obviously many arithmetical sentences that will express this, if there are any at all. And I mean, a special focus will be on self-referential sentences, i.e. sentences that say something about themselves, ascribe to themselves certain properties, and so on. And I mean, this goes back, of course, to Gödel's famous paper on the incompleteness theorem, which we're celebrating here. So there Gödel says we must have a sentence in front of us that claims its own unprovability. So no definite article there. But I mean, in order to evaluate the philosophical significance of all these results, I mean, we really have to say this is a sentence that states its own provability. Okay, and I mean, here is a first rough characterization of what I mean by intentionality. I mean, there are different notions of intentionality out there in the literature. Usually it's much narrower than what I'm doing here. And people just focus on how is provability expressed. But here I would like to say that a meta-theoretic claim, I mean, something like a formulation of the second incompleteness or something like that, is intentional if it depends on which meta-theoretic statement or maybe property is expressed by a sentence or a formula of arithmetic. And then I say meta-theory here, I mean our informal meta-theory that is not arithmetized. So, I mean, we are talking in English with a little bit of symbolism added. Okay, so with this distinction in mind, or its classification in mind, I mean, we can look at certain claims and whether they're extensional or intentional. So when people say every sufficiently strong and sound recursively arithmetical theory is incomplete, this is certainly not a precise claim because I haven't said what sufficiently strong is, and I haven't said what an arithmetical theory exactly is, but that's an extensional result because it does not depend on what certain arithmetical sentences express. Or you have Church's theorem, with the undecidability of logical validity. Logical validity is not decided, but that's an extensional result. It doesn't depend on what arithmetical sentences say. But then intentional results will be of the following sort. The sentence stating its own unprovability in Q is independent in Q and it is true. Well, that's intentional because the sentence, I mean, is a claim to say something. And that makes it intentional. And as a final result, example, the sentence stating its own sigma-1 truth via a specific truth predicate in a specific theory, and we can also fix the coding, the sentence is still refutable. It's still intentional. I mean, it still doesn't pin down one unique arithmetical sentence, and that is because how we obtain the sentence that states its own truth via this truth predicate by standard diagonalization or some other means, that's still underdetermined. So that would still count as intentional. I mean, of course, I mean, your first reaction may be, well, we can make intentional results more specific until it doesn't matter what an arithmetical sentence expresses. So, I mean, this is actually, when you look at a textbook and how the second incompleteness theorem is proved in a textbook, people will start by specifying some fixed coding. So they, I mean, commit themselves to one coding schema. Then in textbooks, you will then find definitions of a provability predicate. So in this case, BWPA, let's say, and then they prove that this sentence, which is supposed to be the consistency, is not provable. And again, I mean, everything is just fixed in a specific way. And that's, of course, then just a mathematical result. And we are proving that a certain arithmetical sentence is not provable. So there's no problem there. But for philosophical applications, we need to know, or for most philosophical applications, we need to know that this sentence here, 0 equals 1 is not provable, that this really means what I just said, namely that it means consistency. And yeah, so I mean, we can really escape this problem of, I mean, determining whether an arithmetical sentence really expresses what it is supposed to express. I mean, a first reaction might be to say, well, the problem of extensionality is only a problem of formalization, I mean, which is everywhere. I mean, there are these informal, imprecise claims in the meta theory, and what arithmetization means is just we have to be precise. But I think there is this formalization problem, but there are other aspects that do not arise in formalization in general. First of all, we have to arithmetize. If we just formalize, we're going from an informal language into a formal language, but they are about the same subject matter roughly. But of course, arithmetical theories are about numbers, not sentences. And so in metamathematics, we have this problem of picking some Gödel numbering. So that's something that is required that goes beyond just formalization. Then very often in metamathematics, we are not given a specific sentence of the meta theory that has to be translated into arithmetic because we are general. I mean, we want to say no theory of a certain sort proves its own consistency, which means that for each given such theory, we need a consistency claim. And so it's not just formalizing one sense, it's maybe giving a recipe for translating. Another aspect that shows, this project of extensionalization is not just formalization, is that very often when we go from an informal claim into arithmetic, we have only limited resources. So, if you want to express sigma n truth, partial truth predicate, then you have to play certain tricks. Of course, when I teach students what's a sigma n true sentence, I say, well, it's a true sentence and it's sigma n. But of course, you can't translate that directly into the language of arithmetic because your resources are limited. You can't talk about the standard model in arithmetic. Okay, so from a philosophical perspective is that many of the philosophical applications of metamathematical results is undermined by intentionality. This has come up in the literature many times in connection with the second incompleteness theorem. People observe that there are deviant provability predicates, Rosser provability, for instance, or Pfefferman's provability predicates, for which the second incompleteness theorem just fails. Does that mean the second incompleteness theorem is, unstable, and only if we choose certain ways of expressing consistency that are as good as the others, we have the second incompleteness theorem? But as I said before, I would like to widen the perspective here because, provability predicates, it's a well-known topic. A result may hold for one specific coding scheme, but not for another coding scheme. And I'm going to give you examples of that. Or a result might hold for one specific way of obtaining self-reference, diagonalizing a formula, but not for others. And when we talk about this sentence stating its own provability, let's say, then we have to ask, well, which one? Okay, and Albert mentioned this already. What we might do is not, just doing more philosophy, but we might do more logic and more mathematics. The obvious reaction is the logician can just show that a result is stable or invariant under a variation of the relevant parameters. So we might try to show whatever coding you use, the second incompleteness theorem will always hold, or whatever provability predicate you use, well, the result will always hold. In some cases, this will not be possible. And in these cases, we need to give a specific argument or a justification for our choice of a coding or a predicate. Okay, so now I will look more specifically at sources of intentionality. The first source, where we can vary things, is the language and the theory. This is actually something I will, suppress. Whether something, a theory or a certain claim holds may depend on which function symbols we have in the language. For instance, in truth theories, there are certain axioms that are consistent in some languages, but if you have too many function symbols, then suddenly they become inconsistent. But I will put that aside. So the sources of intentionality I'm mainly interested in is coding. So do different codings have an impact on the results? I will look at the traditional problem of expressing properties such as partial truth, probability, and so on. And then I will also look at different ways of obtaining self-reference. Okay, of course, which sources are relevant depends on the claim we have in mind. For instance, self-reference will not be relevant for the second incompleteness theorem. I mean, that's simply because the claim we're talking about in the second incompleteness theorem is Peano arithmetic or whatever theory is consistent, and that's not a self-referential claim. I mean, anticipating complaints by certain people in the audience, I have to say, this is of course not to say that, I mean, self-reference does not play any role in the proof of the second incompleteness theorem. I mean, it does in the usual proofs, at least, or proofs we know. But the statement itself does not involve self-reference. Then, what's also very important, these sources are ordered. So first we pick a coding, then relative to that coding, we pick a provability predicate. And if we have a self-referential claim, then relative to that coding, relative to that provability predicate, we then construct a self-referential sentence, for instance, by standard Gödel diagonalization. Okay, so in the literature, different sources of intentionality are usually addressed, I mean, in very different ways, and approaches tend to be very ad hoc because people are interested in specific problems and then, I mean, try to prove some invariance results. And I mean, what people very often do is they say, well, I mean, choose some natural coding. If they're really forced to, they will come up with one specific coding, but then say, well, goes for all natural coding. They will very often talk about natural provability predicates, and it's very well known that it's not clear what that really means. I mean, what also comes up is very often when we construct these arithmetical sentences, we need to formalize quotation in some way. That's usually done using Gödel numerals. So, I mean, the numeral for the code of a certain expression, and this is usually successor of 0. But of course, there are many, many different ways to to mimic quotation to some extent. And when people talk about self-reference, people usually just say, well, use the usual way of diagonalizing, which Gödel invented. But of course, there are slight variations out there in the literature. And I mean, what I'm going to do in this talk is now go through, I mean, these three sources of intentionality. So coding, expressing properties, and self-reference. Okay, so I mean, first about coding. So usually in metamathematics, people fix some coding and prove the results relative to that coding. For instance, that is what Pfaffman did in his famous 1960 paper, Arithmetization of Metamathematics. And this is what happens in the usual textbooks. I mean, when I was first taught the Gödel incompleteness theorem, the lecturer said, I mean, he was aware of the problem of different codings and that, and then just said, well, I mean, as you can obviously see, I mean, the proof of the incompleteness theorems will go through even if you change the coding schema. I mean, of course, the coding schema has to be reasonable. I mean, it has to be effective in some way. So we can still talk about concatenation and projection and so on in the language of arithmetic. But of course, the notion of reasonableness for a coding is hardly ever made explicit. Yeah, I mean, what we should expect from a reasonable coding is that syntactic operations should be computable and, I mean, provably recursive in the relevant theory. And I mean, the first observation here is whether a coding schema is reasonable or not is relative to a given arithmetical theory. So if you work in Peano arithmetic and you have full induction, then you don't have to worry, for instance, about whether exponentiation is total, or if you have a really fast growing functions in your coding, PA will be able to handle it. But if you're interested in very weak theories, say you want to know whether the second incompleteness theorem still holds for very weak theory, I mean, it would be silly to take a very inefficient coding and then prove the unprovability of something simply because your arithmetical theory cannot prove that certain sentences exist. I mean, that are obtained by, taking the conjunction of something, for instance. So the notion of a reasonable coding is at any rate relative to a given theory. Okay, and then I thought I'd give you an example of how results and proofs can be unstable under changes of coding. And here I have, abused, an idea by Albert. Namely, I'm going to show you this proof of the first incompleteness theorem, or an intentional version of the first incompleteness theorem, that goes through without proving Gödel's diagonal lemma within arithmetic. And this is because we shift diagonalization to the coding. Okay, so choose a coding. So we have for every formula of our arithmetic language a number n such that the code of phi of n, so when I put a dash above n, that means this is the numeral of n, so successor of 0. And the code of this is n. So this is unusual because, in the standard textbook codings, the Gödel number of phi of n will, of course, be much, much bigger than n itself. But, it's fairly clear that we can define such a coding. What is less clear is that we can define such a coding and still have all the usual syntactic operations recursive. So, it's in a way, this coding can be designed in such a way, and Albert showed this, that it has all the usual properties that are needed for the proof of the first incompleteness theorem. Now, given such a coding, we can prove the first incompleteness theorem in, without appealing to the diagonal lemma. So, because we have this equation here, now use this for a specific phi, namely for the formula not provable x. And so we have a number n such that n equals the code of not provable n. That's a closed equation and thus provable in even the weakest theories of arithmetic. So we have this. And then we have the diagonal property. So this is the Gödel sentence now. Not provable n is equivalent to not provable. And now we replace n with this. So this is just substitution of identicals. And we have a sentence gamma, namely this sentence here, that is provably equivalent to not provable gamma. Once we have this, then we can proceed in the usual way. Appeal to the soundness, omega consistency of piano arithmetic, and show the Gödel sentence is independent of piano arithmetic. Okay, if you prove the first incompleteness theorem in this way, it would definitely show that piano arithmetic is incomplete. But what about the claim, about the intentional claim, that the sentence stating its own unprovability is independent? I think this proof does not establish that claim. And this is because, it does not go through for other coding schemata. So this is a proof that works only with this very sophisticated coding schema where we have this property up here. And if we had used a different coding, it wouldn't go through. So this is why, we usually diagonalize within the theory. And that has, better chances of being invariant under changes of the coding. So, this is the first example of a proof that is sensitive to the coding. And we always try to do something that is less sensitive to coding. Now here is, another example, arithmetical truth tellers. So this is an example I will use several times because unlike, say, Lüb's theorem, this is a result that is very sensitive to how we set up things. So it's more intentional than many other results. So truth tellers are very often said, when you talk to philosophers and you ask, what about the truth teller, about the sentence that states its own truth? People will very often react by saying, well, that sentence should be treated just like the liar sentence. It should be lack a truth value. It should be undefined. It should not express a proposition or the like. But truth tellers are very different from liar sentences, because we can have truth teller sentence, arguably we can have truth teller sentences within the language of arithmetic. And if it's an arithmetical sentence, you can hardly say it lacks a truth value or doesn't express a proposition. It's either true or false in the standard model of arithmetic. So how do we get these truth tellers? It's well known we can define partial truth predicates. So this is something of this sort here. There are standard definitions in the Hayek-Putlag book or in Richard Kay's book. And this is a truth predicate for sigma 1 sentences, so sentences with one unrestricted universal quantifier and then just bounded quantifiers. And this truth predicate itself is a sigma 1 formula. And it's a truth predicate in the sense that you can prove all the T sentences for all the sigma 1 sentences for this predicate. And under the standard definitions of these partial truth predicates, you can also prove the usual compositional axioms for sigma 1 sentences. So for instance, a conjunction of sigma 1 sentences is true if and only if both conjuncts are true, with a suitable notion of sigma 1 sentence. These syntactic operations can upset what a sigma 1 sentence is. Okay, of course, we cannot formulate a liar sentence. So if we apply standard diagonalization to the predicate X is not sigma 1 true, well, that sentence is a pi 1 true, so it falls out of the domain of significance of this true predicate. But if we just apply standard diagonalization to this predicate here, then the sentence itself will be sigma 1. So the truth teller is a sigma 1 sentence and is within the domain of significance of the truth predicate. So we can sensibly ask, is the truth teller constructed with the sigma 1 truth predicate provable, refutable, or independent? So what Albert observed is the sigma 1 truth teller is refutable. That is the sense stating its own sigma 1 truth is refutable. What I find interesting here is that, in the proof, we use a specific property of the coding. It does not go through for these codings with built-in self-reference. Okay, yes, I should be possible to look a little bit at the proof. We diagonalize in the strong way. That is, we have function symbols. So we have for any formula phi of x a closed term t, such that t equals provably phi of t. Okay, so here's the result. We diagonalize the truth predicate in this standard way, and the truth predicate is of the form, there is a y, theta yx. And this usually means, x is the sentence that may be true or not, and the y ranges over codes of strings of sentences or strings of triples or something like that. So one way to do it is, for instance, to say X is true if and only if there is a string of triples. I mean, the first component of a triple is a formula, the second is a variable assignment, and the third is a truth value, if you look up standard definitions of this truth predicate. Or you might do away with the variable assignments and plug in numerals into the formulae, and maybe not have the truth value. So there are variations about that. But I mean, what will play a role is this assumption here. So if we have a monotonic coding and truth is defined in sigma 1, truth is defined in this way, we will have this property here. So that is, if we have such a, I'm going to call it a verification sequence of an existentially quantified sentence, and of course all is sigma 1, then somehow the witness for this existentially quantified sentence must be buried there somewhere in the Y. So there might be a sequence of triples with variable assignments, but somewhere some variable, I mean the variable V, is assigned a witness. And if we have this assumption, then we can show that the sigma 1 truth teller is refutable. So assume this is the truth teller here, obtained by standard diagonalization, as explained here. Now reason in PA, assume the truth teller is true. So this existentially quantified sentence is true. There's a verification sequence for T. Then there must be a witness. Let Y not be the smallest witness of the sentence. So we have theta Y not T, and we have it's the smallest. So for all set smaller than Y not theta set T. So because it's of the diagonal property, and the assumption, I mean, which I've copied down here, gives us that, well, there is a set smaller than Y naught such that theta set T. But of course, this contradicts the minimality. And I mean, that shows the sigma 1 truth teller is refutable. But that holds only if we have this assumption, which in the end follows from the monotonicity of the coding schema. So yeah, and I mean, this is how I got into this entire field of problems. What does that really show? I mean, do we want to have that this result of the refutability of the sigma 1 truth teller is stable under changes in the coding, and we need to consider also coding schemata that are not monotone? I'm not quite sure. So this is a result that is much less stable than, say, the second incompleteness theorem. Okay, so what can we do? I mean, people usually show, well, I mean, the results we are interested in are very stable and invariant under changes of the coding. But really proving that a metamathematical result is invariant under changes of the coding is relatively hard, because, as I said before, the coding is the most basic source of, the most fundamental source of intentionality. Obviously, if you change the coding, I mean, or you want to say, I changed the coding, but I still use the same provability or truth predicate, and I'm still using the same method of obtaining self-reference. But of course, if you change the coding, you need to change the provability predicate. And to make explicit what it means, well, I mean, not to keep the same provability predicate, but to preserve the structure, or just to translate a provability predicate into the other coding, that's not so straightforward. So what we can do, and this is, I mean, the paper we are working on, I mean, Albert, Bo, Balthasar, is, I mean, a coding schema may be understood as a relative interpretation of a fixed syntax theory into the arithmetical theory. So, for instance, you assign different numbers to different primitive symbols of the language. You can code sequences in a different way, but they're all relative interpretations of some kind. So, I mean, a coding schema is much more than just an assignment of expressions to numbers. I mean, we need to translate concatenation, substitution, and so on. And I mean, this would allow us, all these relative interpretations are the reasonable codings. If we have this, we have back and forth translations between different coding schemata, and this will allow us, I mean, to prove the stability of certain results or the invariance of certain results under changes of the coding. So I mean, this allows us, for instance, to say the second incompleteness theorem is invariant under changes of the coding. And that means we always have the canonical provability predicate, but just with the coding changed. And I mean, I do not really know what happens to the sigma 1 truth teller. I mean, this might fail to be invariant, but we haven't been able to show this. Okay, next source of intentionality. This is expressing properties. So in a way, this is the traditional topic when people discuss intentionality metamathematics. Namely, we have certain properties, such as provability, sigma n truth, logical truth, Rosser provability, but there may be different ways to express these notions. And I mean, the problem first came up when people tried to generalize the second incompleteness theorem, because there you have, I mean, just some extension of Peano arithmetic. And yeah, what does it mean to be a provability predicate for such an extension? And I mean, this was basically, I mean, the first main contribution to this was Pfefferman's arithmetization of metamathematics. And what you very often get in textbooks these days is, I mean, a formula expresses provability if it weakly represents provability. And this probably goes back to Kreisel's 53 paper. So this is not exactly Kreisel's formulation, but almost. A formula BWX is said to express provability in a specific arithmetical theory sigma if it satisfies the following condition. For all numerals n, n is provable can be proved in sigma if and only if the formula with number n can be proved in sigma. So this is weak representability or numerability as Pfefferman had it. Okay, and this is, I mean, Pfefferman's much narrower notion of intentionality. So he writes in the famous 1960 paper, so in broad terms, the applications of the method of arithmetization can be classified as being extensional if essentially only numerically correct definitions are needed, I mean, in the sense of weak representability, or intentional if the definitions must more fully express the notions involved, so that various of the general properties of these notions can be formally derived. So, I mean, the first incompleteness theorem famously goes through just with this assumption on the provability predicate, weak representability, but there are formulae expressing provability in the sense that do not satisfy the conditions, and therefore the second incompleteness theorem fails. I'm not going to say more about the notion of intentionality because that has a long history. And I mean, modern philosophers don't recognize this as extensionality or intentionality. Okay, representability is not really a very useful criterion for deciding whether a formula represents a certain property. I mean, for provability, it's already very questionable because the second incompleteness theorem will fail for certain formulae that express provability according to this criterion. But for other notions that are more complex, representability of this kind, I mean, is useless. I mean, let's say you have pi n truth for, I mean, n bigger than 0, pi 5 truth. Of course, there's no hope that you can have a formula that represents, pi1 truth or pi5 truth in piano arithmetic. It's just too complex. But nevertheless, I think many people would be happy to say no, but it still expresses pi1 truth. And why is that? I think people would justify the claim that these partial truth predicates are actually truth predicates because they satisfy certain meaning postulates. So for instance, we can prove T sentences for all sentences in the relevant sentence class, all pi1 sentences. And so we might characterize whether a formula expresses a certain property by appealing to what we might call, to use Carnap's term, a meaning postulate. I think it works quite nicely for truth predicates, but even there it's not completely clear what exactly the meaning postulates would be. T sentences or maybe also compositional axioms, I don't know. But in the case of provability, I don't believe in this meaning postulate result. The obvious meaning postulates would be the loop derivability conditions. First, you can satisfy the loop derivability conditions with trivial formulae, let's say x equals x, but also something seems to go wrong to say whatever satisfies the loop derivability conditions is a good provability predicate, because how did we get to the loop derivability conditions? It was not that people said from the beginning, obviously, any provability predicate has to satisfy these conditions. It was rather a fairly convoluted process to arrive at them. People looked at good provability predicates. They satisfied the loop derivability conditions. And so the loop derivability conditions came after we had already chosen a correct or a good provability predicate. And then, of course, mathematicians just did what you would expect. It's already Hilbert-Bernays, and then of course, in this specific form, they just generalized and observed all we need for the proof are these conditions. But I don't think they should be used as a criterion. So, the last criterion we might apply is, and this is very often something that is seen in philosophical discussions, we just say, well, if you formalize provability, you do it in a natural way. You don't do weird things such as using a Rosso provability predicate. But again, that isn't that promising. In the case of provability, maybe, but what about sigma 1 truth? What's the natural formalization of sigma 1 truth? It seems to me that the usual textbook definitions of arithmetical formula defining sigma 1 truth are not natural. What would be natural would be to say a sentence is sigma 1 true if it's sigma 1 and holds in the standard model of arithmetic, or is just true. But we just can't do that in arithmetic. So, to sum up, I have really no idea what it means for a formula relative to a given coding to express a property. It all seems to be very ad hoc and piecemeal. Here is another example where we use predicates to express sigma 1 truth. And all these predicates are not engineered, such as the Rosso provability predicate. So what do we need? Just as a background, CT some axiomatic theory of truth, but it's not really important here. So as we said, if we fix the coding, but now we express sigma 1 truth using the partial truth predicate as before, and we said there already, then the truth teller will be refutable. Then another way to express sigma 1 truth is to use the provability predicate for a sub-theory of piano arithmetic. the good thing is, I mean, you can show in piano arithmetic that this formula is a truth predicate and satisfies the T sentences for all sigma 1 sentences. I mean, piano arithmetic proves the reflection principle for, I mean, the subtheory. That's provable phi, then phi, and phi arrow provable phi, that's formalized sigma 1 completeness. And so if you express sigma 1 truth using this provability predicate, well, then you get a provable truth teller. And that follows from Loeb's theorem. And maybe if you use a primitive truth predicate, you get an independent sentence, but that's maybe less interesting. And as I said here, I mean, we can express sigma 1 truth using this, and this is usually thought to be natural. We can use it, express it using provability in I sigma 1, and then it becomes provable, and both predicates are not in any way crazy or weird. Okay, then the last source of intentionality is self-reference. So let's assume the coding schema is fixed. Let's also assume we have decided on a formula expressing the property, but which sentences say of themselves that they have property P. The first idea might be, well, just take a diagonal sentence. Diagonal sentences are somehow self-referential. But this is clearly not the case. I mean, in the case of unprovability, it's not so easy to get diagonal sentences. But in the case of other formulas, it's very easy to get diagonal sentences that are obviously not self-referential. So for instance, if you take truth predicates, I mean, the point of truth predicates is that they have only diagonal sentences. All sentences should be diagonal sentences. We don't have an unrestricted truth predicate in arithmetic, of course, but for instance, all sigma 1 sentences are diagonal sentences of this partial truth predicate. 0 equals 0, for instance, but also 0 equals 1 would be a diagonal sentence of this partial truth predicate, clearly not self-referential. Also, if you take provability, I guess this is something that Henkin was aware of. Well, you can, 0 equals 0 is a diagonal sentence, but only trivially so, because 0 equals 0 is provable, and therefore 0 equals 0 is provable, is also provable. Therefore, both sentences are equivalent. But one would not want to say that 0 equals 0 is a Henkin sentence stating its own provability. This is why Henkin had to ask his question in a more clever way. My suspicion is that people lost interest in self-reference once they looked at the canonical provability predicate and had Loeb's theorem, because I mean, if you have Loeb's theorem, they can actually prove that all diagonal sentences behave in the same way, whether they are self-referential or not. But this, in this case, provability or canonical provability is really a very special case. It's very elegant, it's very stable because all diagonal sentences behave in the same way, but other formulae are not that stable. So, I mean, for these cases, we really need a more fine-grained criterion for self-reference, definitely not just being a diagonal sentence. This is a proposal going back to Henkin and Kreisel in the early 1950s. And this is self-reference via a closed term. So you have a formula phi expressing a certain property given. And then a formula gamma says about itself it has property p if and only if it is of the form phi of t for some closed term t that has the code of phi of t as its value. Yeah, and then of course this implies the diagonal property. And maybe this is a sufficient criterion for self-reference via a closed term. But it can't be necessary because in many languages we simply don't have such closed terms. But we probably still want to say that in Zermelo-Fraenkel or piano arithmetic in the original language we can have self-reference. But results still may be unstable, and you might have two sentences ascribing to themselves a property, and I mean by this criterion, and still they behave in different ways. And I'm running out of time, so I mean I'm cutting this short. I mean, it follows from an observation by Kreisel from the early 1950s that we can have refutable Henkin sentences, so sentences saying about themselves that they are provable. Of course, that can't be a canonical provability predicate because then Lüb's theorem would strike. But I mean, what this result here shows is we have a Henkin sentence in the sense that T2 equals provable T2, so it's self-referential by the Kreisel-Henkin criterion. This is a provability predicate in the sense of weakly representing provability, but the Henkin sentence is refutable. But the T2 term is not obtained by standard diagonalization. It satisfies the Kreisel-Henkin condition, but is not the standard diagonal term. If you apply the usual diagonal procedure, you actually get a provable Henkin sentence. So again, this Kreisel-Henkin criterion is not sufficient for, I mean, narrowing down the sentences that ascribe themselves a property, so that results like the provability of the Henkin sentence becomes stable. So changes in the way self-reference is obtained can still make a difference. So I skip the proof. I mean, just as a small remark, I mean, we have the feeling that the diagonal sentences obtained by canonical diagonalization are in a way the sentences we are really interested in. So for instance, when you look at truth tellers, Henkin sentences and so on, and you ask what happens to them, what happens to the sigma 1 truth teller, the first sentence we will look at are those sentences that are obtained by the standard Gödel diagonalization, not by some trickery like in this observation by Kreisel. And this is something we are trying to make explicit in a further paper. So, I mean, I should wrap up. I mean, what are the conclusions? So problems for the philosophical significance of intentional metamathematical results may not only arise through the way provability, truth, and so on are expressed, that's well known, but also because we might vary the coding and we might vary the way self-reference is obtained. I mean, this won't come up for canonical provability, but if we have less stable results, then, I mean, we will have this problem. And I mean, we might overstretch the significance of metamathematical results because, I mean, they depend on a specific choice we have made. Then the three sources of self-reference I have mentioned interact. I mean, sometimes you can show that, I mean, say we can change the coding, but keep always the standard provability predicate, for instance. We might be more strict on the coding, and that gives us invariance in another dimension, and so on. So this is something I find technically very difficult. I mean, it's not just, I mean, that there are results that are more stable than others. It depends on, they might be more stable in, say, the changes of the coding. Others might be more stable in changes of how we express a certain property. Okay, and then, I mean, we just have to see how far we can get and to what extent we can extensionalize results in proof generalizations. And I mean, we should make clear what we really mean by reasonable coding, expressing certain properties and so on. Okay, I think I'm out of time, so I skip the open questions and stop sharing.